All right, so in this video we're going to have a look at jet flows. So jet flows are very commonly found in many technical applications. So for example, when you want to mix fuel and oxidizer, you're doing that usually with some sort of jet that's going to inject into the fuel into the air. You can also find that, of course, in the jet engine, where it is being used as a thrust device. So there's between these two, there's a lot of different other applications that you can find, and so it is a very important flow configuration, and this is usually associated with turbulence, and it is a very useful sometimes to have the turbulence to improve the mixing between the fuel and the oxidizer. But sometimes you would like to suppress it in terms of noise, for example. The noise that's being generated by a jet engine that flies over your head is usually created by some sort of turbulence that's being created at the orifice of that jet. So what is a jet? Let's have a look at that. Here is a flow visualization from the Technical University of Denmark. So this is a very nice visualization, and that can show you quite a lot of flow features in a jet. So the flow is going to come out of an orifice and it's going to mix with the quiet air around it. And by doing so, it produces turbulence. And the turbulence has different features when, depending on whether you're looking close to the nozzle or a bit more further downstream. So there is a little bit of control that you can provide to the jet so that you can manipulate it so that it can actually improve your technical application. So we're going to get to this video a little bit later one more time. And but first I would like to have a little bit of look at the basic flow pattern or the basic features of a jet. So let's have a look at the round jet. So usually you have some sort of nozzle which is accelerating the flow and going to then direct the flow into a larger, usually quiet chamber. So you have here a flow velocity that we call your jet. So that's the main flow. And if you're now looking at the velocity profile that's as shown here, this one has maybe a slight boundary layer over here, but it's largely flat over here. And here's a small boundary layer. So the flow comes over here, and you have a flat velocity that comes here. And this one should be approximately the jet velocity in the center. So because the velocity is going to be 0 over here, and it's going to be not 0 here, you're going to, when you're going further down, you're starting to mix over here. So we're mixing the flow with the quiet air. That means if you're going slightly further down, you're now creating this sort of mixing layer where the flow is the jet flow is going to have an effect on the quiet air around it. So if you're going somewhere over here, let's say, the velocity profile would be still the same length over here. So that you still have the jet velocity over here. And it's going to be flat somewhere over here. But then it starts to adjust over here. And this is essentially your mixing layer over here. Okay, so still flat here. That means what you're seeing here is that you have here the flow that's flow velocity profile that's curved first to the right over here, and then it turns to the left. So that means you have here an inflection point. And this is what you call a Kelvin-Helmholtz instability. Okay, and that means that your flow is naturally unstable in terms of turbulence and starting to drift into turbulence as soon as the Reynolds number is high enough. So you have, and that is usually very, very early the case, so you need to have very, very low Reynolds number so that it doesn't really occur. So most of the jets that you're going to encounter are going to be turbulent jets because of this instability and because the Reynolds number is usually high enough that this inflection point and this Kelvin-Helmholtz instability then transitions the flow into turbulence. So now if you continue with that, so these two shear layers are starting to grow until they meet somewhere. And then you have a velocity profile that maybe looks over here, something like this, like a bell curve. So if you're now going further downstream, you need to conserve the momentum. That means the center line velocity needs to be, so essentially you're dispersing all the momentum here towards the sides. That means the center line velocity needs to decrease a bit and your momentum essentially disperses all the way around here. So you're still going to have a bell curve, but the center line velocity is going to be a little bit lower than before. Somewhere like this, the mean. So with that we have now our mean velocity profile mapped out. So you have here a region, which is a so-called potential core. Sorry, over there. Where the flow is not really affected, that means you still have the jet velocity, and this one is approximately 6 diameter long for turbulent flows, and is of course not a hard number, it's just a rule of thumb. And then you have the jet-like velocity profile over here. All right, so let's have a look at some of the basic numbers here. So first of all, we need to define our coordinate system, and we define our coordinate system over here. So we have here the radial direction, r, and we have here now in the center the actual direction, which we call x. And one of the velocities we have defined already, the jet velocity, and we have then need to define, of course, the diameter of the nozzle, which we call d. So the first thing we can define, of course, is the Reynolds number, which is then the jet velocity, or the bulk velocity of the jet, times the diameter over the viscosity. So, and that is going to give you then a measure on how turbulent the jet is going to be. So that depends on, of course, your application. And so that is the first number. The other quantity that's actually quite interesting to look at is here the velocity at the center of the jet. So if you walk along here, we call this one now here the u0, which is dependent on x. But it's not a function of r, it's just the velocity at the center of the jet. Okay, here it's probably should be looking more like this here. Okay, so the center line velocity if I plot that here, I have here u0, and here I have x. So if you walk along here, it's not going to be affected by the flow first, so it's going to be still the jet velocity over here. And then at approximately at 6 diameters, it's going to be decreasing somewhere over here, like this. Okay, so the next thing I want to define is the width of the jet. So how wide is it? And what is a good number to define the width of the jet? And there isn't, we are not going to find a good number where on the edges, because, well, the edges are going to be a bit difficult to define, because it's difficult to say, yeah, the velocity is going to be still, yeah, let's say 1% of the jet velocity or the center line velocity. So that's going to be difficult to measure. So instead, we want to define the half width of the jet. And how do we do that? Essentially, what we do is we have a look at the center line velocity. Then we're choosing where is the half width, or the half of the velocity. I'm going to go outwards over here. And then define this radial position over here as the half width, r1 half. This is the half width of the jet, because at this point, half of the center line velocity is going to be attained. If we do that over here again, this one's going to be a little bit wider, so because the center line velocity is a bit lower, but it's a bit more dispersed, so the half width is going to increase the further you go down. So with that, you're going to get then a line for the half width that is maybe going like this. So this is a good measure to see how wide your jet is, and we're going to use that for something else, but what I'm getting to at the moment, in just a moment.